Hello everyone. Welcome to CSC Core Concepts in the series of Artificial Neural Networks. In this video, I am going to demonstrate the working of a neural network model in RStudio. So let's get started. So we have already discussed about the perceptron algorithm, Rosenblatt's algorithm. In case you have missed my video, I recommend you to please go through the video so that it will be easier for you to understand uh, the working of this neural network model. Now, the data set regarding the data set which I am going to use to perform this model is the admission data set, which I have already also used in earlier some of my videos. Now in this data set, it is a classification problem where we have two classes that whether a student will get admission or not. So that depends on three parameters, that is the GRE score, GPA and the rank. So based on that, we have either class 0 or class 1. So let us implement this classification problem using the artificial neural networks. So the very first thing which we need to do is that we have to include the package neural net. Okay, so this is the library file which we have to uh, load. Okay, so let us say my data is admit underscore nn. So we have, it is a CSV file. So let me just create the let me just input the CSV file. So admission data is the name of my file name. So admission data dot CSV. So let us create a data frame admit underscore nn. So there are 400 observations of 4 variables, right? So same here, if I want to see the structure of the data, so let us see the structure of the data. Yeah, so but one thing you have to see here is that here the admission data, you have different types of variables. That is okay. Yeah, so one is that you have the admission is of type integer. It has values like 0, 1. GRE has a different range like 380, 660. GPA has a different range of values 3.61 and so on. And rank has other range of values. Now, in this case, what we have to do is that we have to perform some normalization. So that the min-max normalization, if we are performing, that will do is that, what it will do is that it will normalize all the values in the range of 0 to 1. Understood. So let's say, for example, if I am performing admission NN, first the value is GRE. So if I want to perform the normalization, that is equals to admission underscore NN GRE value. So for any value to be normalized, this GRE minus the minimum value among all those okay, divided by I like subtractive. Okay, you have subtracted it, and this has to be divided by the maximum admit underscore nn GRE minus the minimum of the value. So basically what it will do is that it will normalize all the values in the range of 0 to 1. Understood? So let us do this. So same thing you have to apply to the other variables also. Let's say the other variables are your GRE, GPA. So here you have to perform it for GPA. And for rank. Okay, so all will be, I will show you the data after it gets normalized, that how does this data looks like in the normalized form, so that all of them are in the same range. That's the only reason. Okay, so let's figure it out. Okay, and done. And if you want to see the structure of the data, or if you want to view the data, let's view the data from here. Okay, so if I am going to view the data, you can see all these values GRE, GP and rank, all of them are in the range of 0 to 1. Okay, so I hope you understood this. Now let us for create a neural network. Again, the data has to be divided into two samples, that is the training sample and the testing sample. So we have two samples here we are going to create for the number of rows in admit underscore nn, and replace is equals to true, and let's say probability is equals to C, let's say 70 and 30. So 0.7, 0.3. Okay, so let's say the training data, the first sample will go to the training data. So SD is equals to 1 for all the columns, and test data is equals to admit underscore NN is SD is equals to 2. So let us create these data frames. So we have sampled them, training data. So the training data contains 287 observations and the test data contains 113 observations, right? Now let us create the neural network model, right? So admit underscore nn model, this is the name we can give to the model, okay, is equals to the function which we are going to use in the neural net package is neural net. Okay, so what you are going to do is you are going to predict the admission against the parameters GRE plus GPA plus rank, or you can just put a dot also, that's okay, and data is equals to your training data. Now, since it is a neural network model, what you have to do, you have to create the hidden layer. So let us do one thing. Let us first create the one hidden layer only, having only one neuron. Okay, one neuron, simple. Then you remember in the back propagation algorithm, what we do? We have to adjust the weights here. So to add, first of all, you will pass the data through the hidden layer to the output layer. There you will compute the loss function. So again, based on the loss function, you have to back propagate and adjust the weights. This was the concept. So if you are not familiar with it, I recommend you to go through my video on back propagation algorithm. It will be more clear for you to understand. Now the error which has to be calculated, that error can be calculated using two ways. One is the cross entropy function that we can call it as, that is popularly known as CE, and another is the sum of squared error. So you can either use SSE or CE. Okay. Then linear output is equals to false. Okay. So this is all you have to do to create the model. So just a minute. Response linear dot output. So it has to be written in the capital. Sorry, that was a mistake. Okay. So the model has been created, right? So let us plot the model. Looking at it, you won't understand anything. So let us plot the admit underscore NN model, right? And let us see how does it look like. So you can see, isn't it familiar to you? Yeah. So this is your input. So you can see the first input is GRE, the second input is GPA, and the third input is rank. And what are these? These are the weights on your input. So the first weight is minus 2.21027, second is minus 2.4337. These are the weights. What is this one in blue? This is the bias, right? And this is the hidden layer. Since we have specified only one hidden layer and one neuron, so there is only one hidden layer. Now this is the weight on the hidden layer. This is the bias, okay, and this is the output. So the error is coming, how much error is there? 157.67, still the error is there. And these weights have been adjusted in how many steps? 871 steps has been done. Understood? So if you want to see the output, let us see how does it work. Okay. So output is equals to compute. So let's say the admit model, I am using the model to compute the training data. So we have to see, how my model is performing, but you have to predict. Okay, this is what you are doing, the prediction. So for the prediction, you don't have to give the first column because it is the admit column. Okay, See, the first column is the admit. It will give you the answer. So this is what you are going to predict using your model, right? So let us see the output. So this is the output which is giving. Now what is this output in the form? See, it is in the decimal form. So it is a classification problem. You want the output either as your 0 or 1, right? That we can adjust. That less than 0.5 value will converge to 0. This is all the probability values, and greater than 0.5 will be converging to 1. That's fine. But looking at so many output for 400 values is very difficult. So let us do one thing. Let us just see some of them net result. Okay, let us see the net result of some head. Head means, let's say, only 7 elements it is showing you. Okay, so let's say and in case if you want to, you can see like this. Okay, if you want to see for a particular column, right? So you can see like this. See here, train data. Say let's say you want to see for the second row and for all the columns. So you can see simply for one row. That is possible. So for the second row, the output you got is 1. The GRE score is this. GPS score is this. Rank is this. Understood? This is for a particular row if you want to see. So now one major thing which I want to show you is that how does the node computation work? See, you remember what was the formula? What do you do? Sum of weighted average weighted inputs, weights multiplied by the inputs. So whatever input, GRE had input what? 0.75. The reason why I am showing you this is that what is the input one here? The value is 0.758 something, right? So 1 minute. Yeah. So you can see here 0.758 is multiplied by this weight minus 2.1027 plus next input is what? 0.8103. This is multiplied by this weight plus 0.666 is multiplied by this weight, right? And plus the bias, right? So this is, it will give you some output. That has to be passed under a activation function. Which activation function? Sigmoid activation function. It will pass. The output will be multiplied by this weight. The result will be plus the bias, and then the result will be will pass through the again the activation function. If you remember, right? So repeatedly, I am insisting you to please go through the video, okay, of back propagation. Now, which node I am talking about? Fourth node, right? I want to compute. Let's see, okay, what is the result? So this is node 1, node 2, node 3. This is node 4. So let us see what will be the input value of node 4. Okay, so node 4 is equals to what it is saying. What is the value? What is the bias? Let's see. The bias here is what? 2.3121. Okay, let's see. 1 minute. Okay, 2.3121, that is the bias. 2.3121 plus first input. First input value is what? First input value is 0.75886 multiplied by your first weight. First weight is what? Minus 2.2102. Let's say this is your first one. Okay. Plus second input is what? 0.8103. Let's truncate up to 4 decimals only. Multiplied by your second weight. Second weight is what? Minus 2.433. 33. Okay, let's say. Plus the third input is what? 0.6666 multiplied by your the third weight, that is 3.0345. 0345. This is just to show you the calculations. Okay, nothing else. So this is, it will compute the result. Let's see what is the result in node input node 4. So the value is coming as 0.68 67, right? Now this has to be passed with me with whom? Activation, right? What is the activation function? Sigmoid. So output of the node 4 will be what? A sigmoid function. So 1 divided by 1 plus 1 plus exponent of minus x, right? So it is minus of in node 4. Okay, this is the formula. This is how you pass through the activation. So if you want to see the out node 4 value, you will get this value, right? So this is the value is of course within the range of 0 to 1 because of sigmoid function. Now this is your what? Your in node 4th, right? 4th. Now if you want to compute this output node 5, right? So output node 5 will be computed as what? Whatever is your output here, okay, output of this hidden layer multiplied by the weight plus the bias. So let us have a look here. So in node 5 is equals to what? The bias. Let's add the bias first. 1.4285 plus what is the input? What output we got as the out node? That will be the input. Okay, 0.6652 multiplied by your weight. Weight is 1.4285. Okay, so this will compute the input node 5. So in node 5, what is the answer you are getting? And this you have to pass through the sigmoid function. So out node 5 is equals to 1 divided by 1 plus exponent of minus 2.3787. Understood? So this is your value. So let's see the out node 5 answer. Out node is 0.91. Now what? Let's see. Now this 0.91 is greater than 0.5. Yes. So that means it will converge to 1. We have not written it yet. Okay, we will write it. But we assume that 0.91 it means 1. So what was the admission answer? 1. Remember? So we have done it for the one row. So what did we do? This is the second row. We want to compute whether the answer is correct or not. So this is the input plus this is the input into weight plus second input into the second weight plus third input into the third weight plus the bias. So we got the answer. That is the input of node. Then this has to be passed under a activation function. So what is your activation function? Sigmoid activation function. So 1 divided by 1 plus exponent of minus x. So this is your answer. Now this will act as an input to the output layer. So this is input multiplied by its weight 1.42 plus the bias. Right. Okay. 1 minute. 1.42 multiplied by, yeah, there is some mistake over here. The weight here is minus 3.6184. Sorry. Yeah. So yes, input node 5. So sorry, this is minus 3.6184. Okay, let us recompute it, not an issue. So in node 5, and this will be passed, this answer will be passed as, so it is already negative, so it will become positive. So 0.9784. Okay. Fine. So let's see the out node. Okay. So this is something different answer we are getting this time. So why we are getting it as a different answer is that, see, what happens is when you rerun the program, what happens is that every time, see, this time when I have executed the program again, see, it won't remain same, right? See, if I am executing this again, if you see the plot here, see, last time whatever you got, yeah, wait, just a minute, let me plot it again. See, what happens is that last time whatever you got, yes, see, the weights have changed. Oh, sorry, the bias values have changed here. And this number of steps has also changed. That is 392. That is why when I rerun in between, that time what happened, that the value has been changed. So the calculation will remain same. So what is your GRE value? So if you are looking at the head of 2, let's see, where was our, if I want to see the second data, head of 2, right. So you can see these are the values. Now you can multiply them. Let's say 0.7586 multiplied by the first weight. What is your first weight? Minus 2.2102 plus the second weight, second into the second weight. The weight has not changed. You can just cross verify them. 3.0345 plus the bias, that is 2.3121. Okay, so this is the value which you are getting. You can execute. So input node value you are getting as 0.6867. Right. Now this value has this in node 2 will be passed as an exponent function to your sigmoid function, and you are getting the output node. Right. Now this input node is 1.4. What is the second bias? That is 1.4285 plus the input is your output node 4, that is 0.6652 multiplied by your weight, that is minus 3.6184. So you can see here, this is the answer. Now when you are passing this value to your exponent function, understood, minus of minus x, if you are passing, let's see, you can write it like this. Anyway, you can write it. Okay. So the, sorry, 1 minute. Yeah. So this is giving you a wrong answer, right? Error. So don't attempt to write this way. So if you are saying minus of minus x, it will give you the positive value. You can pass it on. So just a minute. Yeah, so you can see here is that the what output node value you are getting is that 2.73 something, right? Now since we have truncated much of the decimal places, we may get some little bit of error in the output, but you can see here is that it is say almost nearer to your output which we have seen in the head of output, which was computed by our model, right? This was something computed, and this is something which we calculated, like with value 0.7586 multiplied by your weighted values, right, plus sum of weighted values and all. So this is what we can see. This is just for the sake of understanding your calculation, right? Now anyway, our model is going to do the prediction. So what you can do is that prediction 1 is equals to, since the values are in decimal, we can do something like P1. We can say that net result, sorry, we can take in some values that the net result. So P1 is equals to output net dot result. We can compute the net result, and we can do prediction. If P1 is greater than 0.5, then it will go to 1, otherwise it will become 0, right? And based on that, of course, you can create the table, that is the confusion matrix table you can create, and based on prediction 1 and the actual is equals to train data of admit. Okay, so let us see, let us execute all of them one by one. We can see the table we can create, and tab 1 we can see. So this is your accuracy. You can compute 181 plus 20. So good accuracy we can achieve. So you know how to compute the accuracy and the error, that is 1 minus the sum of the diagonal elements of the table divided by sum of all the elements in the table, which we have discussed it so many times earlier. Tab 1. Right, so 0.29. So if you want to see 279, so if you want to see the accuracy, you can see like this. 0.72% is the accuracy. Same thing you can do for the test data also. So we have seen that output of the test data is equals to, you can do the computations, compute, that is the model admit underscore nn model, and data is your test data, but of course not the first column, which will not be passed. And you can see p2 is equals to output underscore test, and you want to see the net dot result, right? So let us see the results for the test data, and we can check on the accuracy also. So prediction 2 is equals to, you can say if else, if your value of P2 is greater than 0.5, then we can say it will give you 1, otherwise it will lead to 0. And of course you can just create a table, let's say a table 2 of the predictions done by the output data and test data, uh, just a minute, test data and for the admit column, right? Let's see, let us have a execution of all these results. Let's say we can create a table. Let's see the table, what is the accuracy of the output. So yeah, so it is giving a good accuracy. So of course you can compute and check all the accuracy of the diagonal of the table 2 values divided by sum of all the tables 2. So this is the error, and of course if you remove only one minus, you can get the accuracy. Now this neural network model which we created is with only one neuron and one hidden layer, and that too having one neuron. Now if you want to increase the number of neurons, okay, so let's say admit underscore nn model. So if you want to have multiple neural networks, neurons, so you can do one thing, you can say admit, you can call the function neural network, and you can recreate the model plus the rank. Okay, data is equals to train data. Okay, and hidden is equals to 4. Now let's see hidden. When you are saying 4 means there will be only one hidden layer, but it will have 4 neurons. Okay, so the loss function is, we want it as linear, is cross entropy, and the linear output will be false. So if I want to plot the model, I can show you the model. How does it look like? So you can have a look at the model. You can see there are 4 neurons in the hidden layer. Now you may want to go for multiple hidden layers also, right? So if you want to go for a multiple hidden layers, then you have to also specify that in each hidden layer how many neurons you want to have, right? So the same other criteria remains same, that training is hidden. Okay, now in hidden layer, the condition which you have to give is equals to C 2 comma 1. What does it means is that when you have two inputs here, that means you require two hidden layer, and the first hidden layer will have two neurons and the second hidden layer will have only one neuron. Let me just show you how will it look like. Okay, so if I am again plotting the same model, let me plot. See, it is taking more amount of time, right? So how many steps? 4, 6, 2, 6, 7 steps. So you have two hidden layer here. This is the first hidden layer. First hidden layer have two neurons and the second hidden layer have only one neuron, right? So you can increase the complexity of the model if you are not satisfied, and of course we got a very low rate, right? So if you have this type of a model, now you can perform the training and testing, and you can see what is the accuracy you are getting. Still you are getting the same accuracy for the training data, almost similar, and the testing is also giving you. And so it is not something like that, okay, if you increase the number of neurons your accuracy will increase. Okay, so you have to work on that. So anyway, I hope you understood, and in case you failed to understood anything, you can write to me in the comment section, and don't forget to like, share and subscribe to CSE Core Concepts. Thank you.